So stress versus strain. Stresses are the forces on the object. So if we're talking about pounds per square inch, PSI, that's stress. If we're talking kilograms per meter squared, that's stress. Strain is the deformation that happens due to stress. So if the Play-Doh deforms and mushes because you pushed on it, your pushing was the stress, the deformation, the mushing was the strain. Both stress and strain can be shown with ellipsoids, but they're not the same. They can also both be shown on Mohr circles, but it's a stress Mohr circle or a strain Mohr circle, and it's important to know which one you're doing because they're both circles, but they're different. So the stress ellipses versus strain ellipses. Rather than just tell you they're different, I'm going to show you. In the stress ellipse, the long direction of the ellipse, kind of like the pointy long ends of a football, is the greatest stress. That's your sigma 1. Your least stress is your sigma 3. However, where you have the greatest stress is where you have the lowest elongation, usually negative because it's compressing. So the ellipses are kind of backwards of each other. So if you start with something nice and spherical, a nice spherical concretion, these exist a lot in nature. That's why I'll reference them a lot today. And you stress it like this. So which direction is the most stress coming from? Sigma 1, the vertical direction. So basically, you've got a whole bunch of stuff piled on top of it. Sigma 2 and 3 are lower. They're basically confining pressure from material around it. And sigma 3 is smaller than sigma 2. So this particular stress ellipse on the sphere is going to make it look like this. It's squished very much vertically, and it bulged to the sides more in the sigma 3 direction, left and right, than it did front and back in the sigma 2 direction, because sigma 3 was the lowest stress. So the ellipses both tell you greatest and lowest, but they're opposite orientation for the same circumstance. I'm quite sure that the stress ellipse will be on your final exam. I don't know if a strain ellipse will be, but you can always tell them apart because stress is with sigmas and strain is either showing the lambda or showing E. Yep, the little E epsilon for elongation. So you covered before there are a few kinds of strain. There's volumetric strain. The whole thing shrinks or expands depending whether it's compressive or tensional. It could be you have a sponge and you squeeze it. It gets smaller because of the compressional stress. It could be a balloon. Take a balloon and dunk it underwater. First of all, kind of hard, but second of all, if you get it under there, it'll actually compress because of the stress, the pressure on all sides of the balloon. If you take it outside in the winter here in Grand Forks, it will shrink because of the pressure created by lowering the temperature. Air pressure outside stays constant. Pressure inside the balloon decreases as it gets cold because the gas contracts. Therefore, it's a pressure compressing it and makes it shrink. All three axes have pressure. All three axes have similar pressure, or at least enough that it doesn't bulge out in one direction. It compresses in all directions. Shear strain. Due to shear stress, it's like Play-Doh or a deck of cards or textbook. If you push across it and it shears and gets this angle like this, that's shear stress being applied, and then the strain is the displacement. Gamma is the symbol used for shear strain, and what it represents is the tangent of the change of angle. So like right here on the spine of this textbook, it moved from straight up and down to this angle. That's tau. Take tangent of tau and you get gamma, which is the shear strain. We will use gamma in today's lab, so probably make a note of that equation somewhere on your lab paper or something. And I can always bring slides back up if you need it. Okay. Longitudinal strain. This is from stress in one direction. Elongation or compression are both longitudinal strain. So if you compress it or stretch it, it'll either expand or shrink depending on whether your stress is positive or negative, compressional or tensional. No volume change accounted for. So even if you're dealing in 3D objects, you'll have some stress in the other directions. Even if it's just air pressure, there's some stress. So you squeeze in the direction that you are focusing on or pull. Technically, there's probably some volume change, but this doesn't account for it whatsoever. All we care about is the elongation in that direction. So lowercase e or epsilon is elongation. And this is one of the two ways that you can calculate elongation. I have the other way coming up shortly. But so length, which is the current deformed length, minus length naught or length initial, divided by length initial. So normally when you have something that's deformed, you don't have the pre-deformed state. You have the object right now and it's deformed. So you have to estimate what it used to be based on geometry or knowledge or lab handouts. The other strain type, which is in the textbook, although I don't think it was talked about in lecture because we were going to talk about it today, is called quadratic elongation. This gets lambda as the symbol instead of E. This is specifically for use in Mohr circles. We do lambda 1, 2, and 3, kind of like E 1, 2, and 3 for the elongation in different directions of the ellipse. And there's two ways you can calculate lambda. If you have the length and the length initial, you can use this equation. If you have elongation, which requires length and length initial to calculate unless you're given E directly, then you can calculate it with the second equation. And they are equal to each other. And down here I also have the other formula you can use to calculate E. If you have a percent change, you're like, it increased 200%, instead of saying it tripled in length or doubled in length or is 43% longer. We focus on different ways that it gets said, because if you're reading something or somebody's talking to you, different people will say it differently, and it means a different mathematical representation, and that's important to interpret. So part of the lab is kind of focus. I say it different ways in the lab, and you have to make sure you're coming up with the right way of writing the equation. So Mohr circles for strain. Next week we do stress Mohr circles. So it's important. We're going to use lambda. And it's showing the relation between longitudinal strain, that elongation, and shear strain. So we use something called stretch. When you have one of these ellipses, we label them with lambdas or e's, but the actual length that you draw to have it be appropriate is using s, the square root of your lambda. And so those ellipses, if you are given an ellipse on a axis and you have to read it, you'll know that it's s, and then if you want lambda, you have to square that value. So if it comes out to 3 on that lambda 1 axis there, it means lambda is actually 9. And just like before, since E1 is greater than E2 is greater than E3, means S1 is greater than S2 is greater than S3, and the ellipse is always drawn in this orientation. So your strain ellipse is always laid out this way, unless for some reason they decide to change it to be real-world orientation, but they need to identify that when they're setting up the figures. Now, we also use a lot of primes. Prime indicates it's the messed up, deformed situation. So lambda is, your circle. Lambda prime is an ellipse. Or, lambda is a square and lambda prime is a rectangle. It's deformed. So anytime it has a prime mark, that's the after deformation, which is usually present day condition. The axes that we're going to plot these stress Mohr circles on are lambda prime and gamma prime. The lambda prime is your x-axis, gamma prime is your y-axis. And to get lambda prime, which is, for these axes, even though I put them on the same slide because it's a little confusing, but this lambda prime for the axis is different than this lambda prime. This lambda prime means the deformed quadratic elongation. This one is the axis that mathematically is going to turn this into a circle instead of some other weird shape. And it's 1 over lambda. Gamma prime is gamma, your shear strain, divided by lambda. So if you were going to draw this, you would have to measure different angles and take the tangents and so forth. But happily, you don't have to do that. You can actually get those off of here without ever calculating those. All you have to do is plot 3 points and have a compass. And then you can read things off of it without doing the math. You plot lambda prime 1 and lambda prime 2. So if you have something, you have an ellipse, you can measure the values, you figure out, hey, this used to be circular, so I know it deformed by this percent and this percent, calculate elongation, use that, calculate lambda, 1 divided by lambda for the 1 direction and the 3 direction, and you have the 2 points. Your third point is the center between them. Throw your compass on the center, draw a circle that touches those 2 points. As long as you found your center properly, it'll touch both points. And you've drawn a Mohr circle. Oops, back up. When you're drawing that Mohr circle, all the points around the edge have a value in the xy coordinate system. It's a lambda prime and a gamma prime. So you can read off of it and find gammas, you can find shear strain without doing the trigonometry. So if you have a circular concretion in a sandstone bed and tectonic activity happens and it folds it and squishes it, the concretion is going to get squished along with the sandstone. You can use a Mohr circle to measure how much it got squished, how much distortion there was. You can then use that information to correlate the distortion on other things, because not everything starts out circular. Certain kinds of concretions are really helpful because they always form spheres in cross-section, circles. So if you have a fossil next to a concretion and they're deformed, they probably deformed almost identically. Figure it out for the concretion, and now you can recreate what the fossil used to look like. You can also use it to calculate the stresses. Stress fields are a big deal for certain engineering jobs. Petroleum engineering, for example, worries a lot about stress fields when they're drilling. If you have the strain, you can find out what stresses have occurred and figure out the stress fields that way sometimes. So you have something that looks like this. It's a squished concretion sitting there in the middle of this big white limestone formation. This is the concretion, not your Moore circle. And you find a point right along the long axis, and you find a point anywhere else. I mean, if you had a concretion in your hand, you could literally put dots on them if you wanted to. Measure the angle between them from center. We call this phi prime because it's currently deformed, so it gets a prime. From that, you can find out what the angle used to be back when it was circular. This will give you the angular distortion. You can then apply this to other objects nearby. So this equation here, important note, we're using lambdas, not lambda primes. So that equation there tells you what the original angle was for the same point. So this is where I brought Play-Doh. So got a nice blue concretion with an orange dot on it. And so if I start here and you say, okay, it looks like, that angle from center to the side is maybe 50 degrees. I apply vertical pressure. There's also, of course, confining pressure, air pressure. Squish it down, and now my orange dot has moved. It used to be up here, now it's down here. If you look at the angle it forms, it's a smaller angle now. I don't know, probably 32.5 degrees. Yeah, I'm going to go with that. But if I knew how much I had squished it, if I had a caliper and measured it in the vertical and horizontal directions, and then measured again after I smushed it, I could back calculate exactly what the angle was and know precisely where this point in space was before I distorted the Play-Doh. Now, if I had other things in the formation nearby, I would be able to apply the exact same angles that I got from my circular thing to them and recreate what they should have looked like. On the Moore circle, you can put that point. Now, this circle is just based off lambda prime 1 and lambda prime 3. Find the center and draw a circle. Phi prime, that angle, if we double it, draw it from the left specifically, so up to phi prime up, and put a point. That is in the deformed state where this orange dot is on my Play-Doh. I can read the values from P prime and say up 1.4 gamma prime and 0.9 lambda prime. Gamma prime is just gamma over lambda, which means I can calculate lambda from lambda prime and then get gamma, and now I know how much shear happened to that. Because even though I wasn't applying shear pressure, it was straight down, the spherical object had things moving sideways. So shear happened to it, and you find out how much shear happened at that edge of the circle. And I believe that's part 3 or 4 of today's lab. You actually have something that was squished, and you calculate, hey, how much did the thing shear? How much did it move? Well, not a physical length, but a shear stress value. So as an example, do you guys think this trilobite was squished, or was this its original shape? Trilobites are kind of exotic looking, and there are lots of different forms. So maybe it was squished, maybe it wasn't. It looks kind of regular shape, though, especially if you've seen trilobites before. How about these? That one's a lot squatter looking. Its legs in the middle are really close together. Or this one, very long looking. Or that one. How do you know for sure? What if it's a new species? What if it is just distorted? If you don't have any frame of reference, you don't know. You could guess. It could be an educated guess, but it would still be a guess. If you had spherical sandstone nodules, spherical hematite nodules, spherical limestone nodules, any of these different things that always form spheres, and they were in the rock near the trilobite and they're distorted, suddenly you know whether the trilobites are distorted or not. It's one of the ways that I'm more familiar with. I did my master's work in paleontology, so I keep throwing fossils up here. But how much was it distorted? This guy here, should he be 3 times as long and be kind of like this? Or should he be just a little longer and be kind of like that one? I don't know. So you need a reference, like I was saying, a frame of reference to know how much distortion happened.